Okay, eigenvalues and eigenvectors, the next thing in Math C. So I'll explain what they are and what an equation looks like, and another sort of way to look at it graphically, and then we'll solve it. Okay, so just going back, it's similar to Markov chain. A Markov chain, we had a transition matrix times x equals x. That was how you, to solve for your steady state. So in this Clinton-Trump example, we solved this equation here. Okay, so eigenvalue, eigenvector is similar, except we have this extra thing, this multiple. This is a scalar. Okay, this is just a number. So it could be any number. It could be 5. It could be -8. All right, and again, we've got our transition matrix, so we're normally using the letter A. At least that's what they use in the textbook. So this is the transition matrix, and we're given that. Okay, transition matrix is a given. We're given the matrix, and we have to solve to find these two things. The scalar, this is a scalar, and this is the eigenvalue. And we have to find x, which is the eigenvector. Okay, we're dealing with matrices, but we sort of, matrices and vectors are kind of interchangeable. So let's have a quick look at what this looks like graphically. Okay, here's an example. Here is our transition matrix A, and I've just picked a random point, 2, 1, for my x. Okay, if you recall, last year we did these transition matrices, these 2 by 2 matrices for, say, rotating a point, reflecting a point, dilating, stretching, shearing, etc. So any 2 by 2 matrix, if you just make up some random numbers, it's going to do something to a point. If you think of this 2, 1 here as a point on the xy. Okay, so if you recall this. So 2, 1 looks like this. It's over 2 on the x and it's up 1 on the y. And for this particular matrix, if we multiply out, what we get is 8, 6. And if you look, so all of these points, we always make a vector from the origin to think of it as a vector. So now, if this was a eigenvalue, if x was an eigenvector, the equation would have to satisfy this. So there would be some number, lambda here, okay? Well, let's say this was 4. So this 8, 6 is almost a multiple of 4. But a multiple of 4 exactly would be 8, 4, okay? It would be in the same direction. So 8, 4 would be down here somewhere. So it would have the same slope. So it points in the same direction. So this is what an eigenvector is a vector that doesn't change direction. It might stretch, it could flip and go the opposite direction, down this way. But it's not going to change its basic, the slope of that line is not going to change. But in this case, this 8, 6, it has changed. That means that 2, 1 is not an eigenvector of this matrix that we're looking at. Alright, so we want to find one that is. And there may be more than one. So let's go back to our equation. And if we start to solve this equation, ax equals lambda x, we can minus lambda x, and we get 0, although this is a funny 0. This is actually 0, 0, or it could be 0, 0, 0. You can do 3 by 3. 4 by 4, or whatever. Alright, so to solve the one we're looking at now, 1622 times xy minus, now this is where we have to rewrite this as lambda times by the identity equals 0, and what we do is then we can subtract, so we get 1 minus lambda, we get 6 we get 2, and we get 2 minus lambda times x, y equals 0. Put this down here. Okay, we haven't yet looked at something like this, but I will tell you now and explain it later. The solution to this is when the determinant of 1 minus lambda 6, 2 minus lambda is when the determinant equals 0. And I'll come back and explain that at the end. But this is the working you have to do. All you need to do is say, okay, this determinant is equal to 0. So that means that 1 minus lambda times 2 minus lambda minus 2 times 6 equals 0. And expand it out, 1 minus 3 lambda plus 2 lambda squared minus 12 equals 0. And lambda squared minus 3 lambda, no, that's not a 1, is it? Minus 10 equals 0. And so good old factorizing here. Lambda minus 5, lambda minus plus 2 equals 0. So, lambda equals 5 or negative 2. So these are the eigenvalues. Okay, now for each of these, there's going to be an eigenvector. Alright, so for lambda equals 5, we're going to find eigenvector. So we want to solve ax equals 5x. So we want to solve, and we'll just make x equals ab for now. So we'll find a and b to find this vector. So we've got 1, 6, 2, 2 times ab equals 5 times ab. And if we just expand this, and I actually only need to expand the top, you will find that you get exactly the same thing if you expand the bottom. And this works out to then 6b equals 4a, b equals 4 over 6 times a, and b equals, just simplify that to 2/3 of a. And that's it. There's not a specific with exact value eigenvalue, but it's the eigenvalue. Okay, so the eigenvalue, so vector for eigenvalue 5 is this a 2/3 a. So any vector that has that form. So this could be 3, 2, 6, 4, negative 1, negative 2/3, etc. Okay, these are all possible eigenvectors. They all have the same, if you were to plot those, they all have the same slope. Alright, so the next one, now for minus 2, we're going to find the eigenvector. So we solve. Ax equals minus 2x. Again, x is ab. And 1622 times ab equals minus 2ab. Solve this and see. Multiply the first row. A plus 6b equals minus 2a. Rearrange 6. 6b is minus 3a. B is going to be minus a half a. Alright, so A minus a half A is the eigenvector corresponding to eigenvalue minus 2. So any vector that's in that form, so 4 minus 2 minus 10, 5, etc. So just quickly look at, so we're actually done. That's all you need to find, but I'll just have a look and see what this would look like. 3, 2. Okay, 3, 2. We're over 3 up 2. So 3, 2 is here. And 3, 2 corresponds with eigenvalue 5, which means if I multiply this out, it should be 5 times. It should be 15, 10, which it is. If you multiply this out, you get 15, 10, which is exactly 5 times this, and which is going to be way out here somewhere. But the point is it's going to have exactly the same slope. So it hasn't changed the direction of that vector. And the last thing, and not all of you might want to watch this, but I'll just show you why this determinant equals 0 solves this problem. If I can remember how to do that. Okay, I think I remembered. Let's see. Ax equals lambda x, and we rearrange. Anyway, we get, basically you end up with this, lambda I times x equals 0. And normally what you would do in something like that is you would find the inverse, apply the inverse, so you get minus 1 a minus lambda I inverse times 0, right? It cancels, so you get just this, x equals that. Okay, but of course we're timesing by 0, so it's going to be 0, but we know, it's got to be something. It can't be 0. Well, maybe it could be, but it can't always be 0. But the thing is, this inverse, that's if the inverse exists. If this a minus lambda I is singular, of course the inverse doesn't exist. And when it doesn't exist, it's like it's undefined. And when you times undefined by 0, sometimes you get something. That's one quick explanation, but that's not the proper one. Well, let's just start with this. Okay, if we have A, B, C, D this is our matrix A. We times by x, y, and it's going to be equal to lambda times x, y. Right? Of course, the determinant thing is going to be, we're going to have A minus lambda C, B, D minus lambda. It's going to be A minus lambda times D minus lambda minus B, C equals 0. Okay, this is what we're trying to prove here. Okay, that the determinant is 0. So we'll just multiply this out. Ax plus by equals lambda x, cx plus dy equals lambda y. So from this we get a minus lambda x equals negative by. Let's write it that way. And from this one we get cx equals negative of d minus lambda y. It's kind of confusing the way I did it there, but you'll see in a minute why. And if I just divide these equations, okay, just divide, we're going to have a minus lambda x over cx equals negative by over negative d minus lambda y.